Hello everyone, welcome to our presentation. Today we're going to talk about some physics application of surface integral. Well, I'm pretty sure many of us are pretty familiar with surface integral right now because we covered that in chapter 17. In chapter 17, we know how to calculate the mass, center of mass, and movement inertia using surface integral. I hope the equations on the screen look familiar to you. Here's how we find the mass, center of mass, and the movement inertia. Let's do some review questions before we move on. Well, let me get one thing out of the way. You should be able to do this question. In fact, you should be able to recognize this question because I copied this question from our textbook. The only way you didn't know how to do this question is you copy your homework from the answer key. If that's so, I wish you best luck in college. Here's my work on number 1. This is mass equation, and later we replace our density equation with actual numerical equation and replace our differential elements ds to dA. Later, we change our rectangular coordinate to polar coordinates.
Then, from this point now on, we just do the math, and later we will get the answer 108 times pi times root 2.
Second question should be pretty easy. If you do the math, then you should get this as your answer. Now, that's enough for reviewing. If this density function represents charge density, then total Q is equal to the surface integral of the charge density. Here are more applications regarding surface integral that we didn't go over during the class. Using surface integral, we can also find the force of traction, the pressure, the flux, and last but not least, the Gauss's law. Let's start with the force of traction. This equation right here, you might learn this from your physics class. It is called Newton's law of gravity. Always saying that the force exerted between two objects is proportional to their masses and inversely proportional to the square of their distance. In this scenario, we have a particle with a mass of little m, and we have a surface with mass of m2. Now, at this point of the game, we should be very familiar with how to calculate the mass using the surface integral and the density function. In this case, we can find the mass of this surface S by taking the integral of its density function. Now, if we combine these two equations, we get the black equation right here, which is used to calculate the force between a surface and a particle. Now, let's do an example together. Find the attractive force between the hemisphere of radius r with a constant density u0 centered at the origin at the point mass placed at the origin.
The way I approach this question is I first define a vector between the origin and this little area called ds.
I call it E0. Now, E0 is a unit vector which I can define as x over r, y over r, and z over r. Second step is that I divide the total force into little force element called dF. Then I find the relationship between the dF and the rest of the components. In this case, dF is equal to the gravitational constant times the mass 1 times the mass element of the surface all over the r squared, and also multiply the unit vector. And this equation simplified to this equation down here. Our mass functions is equal to our density function times ds. Now we establish this relationship, we can plug this relationship back into our original equation and take the integral of the both sides. After we do that, we get the black equation right here. Now, since the surface is a hemisphere, the best way to solve this integral is to convert ds into spherical coordinate. The substitution is right here. You might also notice, due to symmetry of the force in S components is equal to the force in y components, and solving the integral, you actually get the force of x component and the force y components are both equal to 0. Now we move on to the force in z components. After you do all those maths right here, you should get the force in z component is equal to pi times gravitational constant times the mass of particle times the density function. Since fx is equal to fy is equal to 0, then our total force is just only the force in z direction, which is pi times the gravitational constant times our density function times the mass of particle. Now we know how to solve gravitational constant. Finding actual force is same as finding gravitational force, but to find actual force, we have to use something called Coulomb's law, which is just a restatement of the Newton's law of gravity. In Coulomb's law, the electric force is proportional to the charges of two objects and inversely proportional to the distance between two charges. Now, let's assume U0 is charge density of a surface. Then, the charge of the surface is equal to the surface integral of the charge density. Then we can make the same substitution by substitute the charge of surface into the Coulomb's law, and we get this red equation right here. Now, moving on to something called pressure force. Well, pressure force is not that special. Assuming PR is just pressure force acting on a surface, then the total force is you just taking the integration of all these little forces combined. Now we have reached a very important aspect of surface integral, which is calculating the flux. There are different types of flux. We have magnetic flux, electric flux, the fluid flux, but in my presentation, we are just kill me. In my presentation, we only gonna talk about the fluid flux. In this case, flux velocity. The concept is the same. If VR is flux velocity, then the Greek letter psi represents the volume of fluid per unit of time. Let's do our last example. A fluid is moving along a cylindrical pipe of radius r with velocity field v equal to CERK, where k is the unit vector along the axis of the pipe in the direction of flow. R is the distance from the axis, and the C is a constant, calculating the fluid flux through the cross-section of the pipe. Okay, we have our basic equation right here. Now, after we make substitution, we have the equation right here. As always, the math is not the important part. As long as you know how to set up the integral and calculate it. In this case, we convert into the polar coordinate because it's cylindrical shape. So, after you did all the math, which I ignored, you get this answer right here. The volume of fluid per unit of time. At this point, I have finished my presentation. Now I'll hand the mic to Darren, which he will explain Gauss's law using surface integral. The reason why I didn't do Gauss's law is because I'm so sick of it after taking a semester of AP Physics.
Before we go straight to Gauss's... Before we go straight to Gauss's law, I'm going to talk about electric flux. Today, I'm going to talk to you about flux. So, I'm going to talk about what is flux and its connection to surface... Wait, hold on. Its connection to surface integrals and also Gauss's law. So consider a region of space in which there's a constant vector field. What would be the flux of the field through the square right here? Huh? What is this? I don't get anything. Well, you should think of flux as the amount of stuff flowing through the area. To figure out that thing, we need to know the strength of the field and the area of the thing is flowing through. So if the field strength is say like K, the flux will equal to K times the area of the thing, which is see the side length is L, so it's L squared. Okay, that's pretty simple, right? What about this one? What is the flux? It's nothing! It's not. There's nothing going through the thing. So of course there's no flux. Hope you guys got that on your AP Physics test. Actually, I didn't take the test. I think Magic probably did. Just say. Anyway, moving on to cooler stuff. Okay, so what if there's an incline and it looks something like this? Divide them up to components and ignore the y component. Bam! Easy! Wow, physics is a lot easier than... What is that? Gauss's law, the general law that applies to any closed surface. Any closed surface? Yes, any surface. And Gauss's law states that the outward directed surface integral over an entire closed surface is equal to the net charge enclosed by the surface divided by a permittivity constant. That thing is also called an electric flux. Seems pretty straightforward, okay? So now, let's apply all this stuff to the stuff we talked about earlier. So this is still the vector field, but now it's an electric field. So what does that do? Let's apply what we've learned. And let's see. The integral over the surface. It's just electric field times the area. EL squared. And what about this one? This one's still nothing because it still doesn't go through anything. And this one is, it's just EL squared cosine theta. The only thing to change is now we say it's an electric field. It's nothing. And that's all I have to say about electric flux and Gauss's law. Okay, now, where is Magic? I need to find him.
I'm so dumb with that kid. I need to get my revenge.